Welcome back, nerds and nerdettes. What was that? You thought that it's going to be another 3 months before you got another episode? Well, you thought wrong. As I may have mentioned in the last one, or the original voiceover for the last one, sometimes I do a couple voiceovers, let's be real. I had way more footage than I thought I did for that last episode, and really I have this and another episode's worth of footage that I can get out. So why don't we go ahead and do that? Buckling down here, we've got a couple of things just to get warmed up on and get out of the way before we get to the really hard part that everybody's been looking forward to, which is me actually doing a deeper dive on the electronics. So, yeah, landing gear bay. This should look familiar, actually. The induction tube that you can see on the right-hand side green painted part, that's the top of the landing gear wheel well. It should look very familiar because it's essentially the same thing that I custom made and printed for the Revell Memphis Bell kit. So, I'm not crazy. That's what the actual part looks like. It is a kind of interesting contour, but anyway, beside the point, back to focusing. At the start, you saw me drill the channel that's above that contour molding, since the back of it's actually hollow, which is really nice. There on the top of the screen, actually, you can see a picture of the actual one in the actual aircraft. And I went and saw that airplane. That one's the aircraft that's in the Air Force Armament Museum next to Eglin Air Force Base. I got to visit it recently, so I decided I would take a couple of reference pictures. And landing gear wheel well was one of them. But anyway, back to the HKM kit. So the back of the induction pipe in the landing gear wheel wells is thankfully recessed and hollowed. There are some kind of stiffener braces or ribbing of plastic that runs through them. More so at the ends, which is very easy to drill through. And so using my handy-dandy Tamiya handheld drill, I went ahead and just drilled that out. The inboard motors, similar to the Revell kit, the electrical wiring is going to be running through that channel just to conceal it. The outboard motors, it's not an issue. It'll just pass straight through the nacelle, and no need to disguise or hide it in any way. It can just sit free in the wing. So, once we get the landing gear wheel well together, the intent here is we'll move through into the start of the electronics, how power is brought into the model, then how it's incorporated into a circuit board in the wing, how the motors are tied in. I'll discuss the programming a little bit. I am going to include my programming in the text description for the video because I think it's a really cool way to bring this project to life. I hope you agree. I hope that's one of the reasons you're here. And I'll put a timestamp in the description as well if you want to go ahead and get started or skip forward to when I do the electronics and when I get a little bit deeper into that. If you want to meet me there, perfect. If you don't, stay tuned. So, kind of a regular story. We're using some Alclad paints over the gray green, just to bring out some more detail there. The HKM kit does have a fantastic amount of detail in the gear base, and as I've mentioned before, I'm a landing gear engineer, so detail in gear bays is really cool. And also the B-17's landing gear I think it's pretty cool. The way it works is very interesting because it's an electrically driven, basically giant lead screw linear actuator that drives it. And it can be manually driven from inside the cockpit through a manual crank that turns the lead screw, and the lead screw extends the downlock linkages. Downlock linkages obviously being the geometry that keeps the gear down. So it'll drive it down until it locks into the over-center position. What's an over-center position? Think about your elbow. When your arm is straight out, and for those of you who have the interestingly weird elbow joint that allows you to extend past 180 degrees, think of that and then push against the wall, right? So once your elbow is hyperextended, it's going to want to continue to hyperextend, but the anatomical structure of your joint prevents it from extending any further. So that's essentially what an over-center lock is, and that's how most landing gear systems on pretty much every airplane with a retracting landing gear work. We drive them out until the links go into what we call the overcenter lock, and then the gear is rigidly held in place and is able to absorb, high landing loads without buckling that linkage and causing damage. Anyway, moving back to the actual model, aerospace engineering dump over for now. Although I am absolutely willing to do a little bit more of that as we go. I'll probably talk about it a little bit more in the engine side. I did kind of mention in the last video about discussing how the B-17G is like the ultimate B-17 and the final revision of it, so I can do that. But quickly, I want to talk about the gear bay first a little bit. There's some nice molded in details here. There's hydraulic and electrical lines. You're going to have hydraulics for your brake system, obviously, and then electrical, we've talked about the landing gear extension. And not to mention, right, so going back to aerospace design here, and I talked about it a little bit on the Revell kit, right? The inboard nacelles, there's an engine at the front of the inboard nacelle, then I have to cram a landing gear system in, and then I've got wing structure behind it, right? So we've got a lot of compromises going on. The turbo supercharger for the Cyclone engine that's in that nacelle is aft of the landing gear. I have to run the exhausts back past the landing gear system to get to the turbo supercharger. Then I have to run the turbo supercharger output, which is the engine, the engine induction air, which is through that tube you can see there. That has to go through the top of the landing gear wheel well. It's all just to compromise the design, right? So that makes the landing gear wheel well very busy. There's an oil tank in there for the engine. You want it somewhere that's accessible, that allows you to work on that portion of regular maintenance for the engine without having to do a ton of disassembly. Again, warplane here. We don't want regular maintenance tying up the maintenance crews when we're getting aircraft like, Yield Pub that are getting halfway cut in half, and we've got other aircraft that are getting, flight control surfaces blown off and holes put in their flight controls and holes put through their structure, through the cockpit, and through the crew cabin. Not a nice thing to think about, but again, it's a very real thing to think about that these maintenance crews had to deal with. So the easier that maintenance can be for the aircraft, the better. So yeah, here you can see the oil tank that goes into the wheel well. Again, it looks relatively familiar for the one that I made for the Revell kit. It's not an exact match, but I'm happy with the one that's in the Revell kit for now. It adds a good amount of detail, and once I finish populating that landing gear wheel well with plumbing, I think it's going to look fantastic. So one each side, of course. Really easy to do. So on the subject of Ultimate B-17s and engines, right? So as I mentioned, Texas Raiders is a very late model B-17. Mentioned that in the last video. Go back and watch it if you don't believe me. And then, like and subscribe. Leave a comment, say hi, tell me a story. Anyway, late model B-17. So we've done a couple of revisions, but one thing that stayed permanent is the Wright Cyclone engine. So why is the Wright Cyclone engine permanent here? Mostly it's to do with the snowballing effect of what happens when you start changing big things on aircraft, right? So with piston engine propeller driven aircraft, there is a limiting factor to how quickly you can spin the propeller. And that limiting factor is the speed of sound. Once you get supersonic, weird things happen, right? So you end up into air compressibility, fluid compressibility effects. Not to mention you're now generating sonic booms at the propeller tips, which is why you can hear when a B-17 or another piston engine aircraft with a high horsepower engine goes to full throttle, the sound gets a little bit different. It gets quite intense. You can hear it also in your jet airliners as well when you're at full throttle on takeoff. Right, the blade tips and the propeller tips of those respective engines are supersonic, and you're getting the sonic booms as part of the noise profile for the engine. And it's annoying, and it's harmful, it's damaging, and it isn't efficient if you're not designing for it. And it's very difficult to design a propeller or a fan that's efficient through the entire regime. So in order for a higher horsepower piston engine to be effective, you have to have a bigger, more aggressive propeller, which means now you need additional ground clearance, which means this landing gear strut that I'm painting right here needs to be even longer, and then you just get a snowballing effect, right? So that's why we didn't re-engine the B-17s ever, and you look at the B-29 and you see that its structure is very different for an engine that's essentially twice the size of the Cyclone, and you can also see the propeller is enormous. Again, you want to take advantage of that extra power, so you put a bigger propeller in there because we want it rotating roughly the same speed when everything's said and done. Okay, I'm going to continue just talking about the model for the rest of this video. My aerospace engineering dump is finished. If you want more, throw a comment down, let me know, indicate it, communicate it to me somewhere. I am happy to share. So the struts I'm doing in bare aluminum. I have seen some B-17s with white ones. Again, the aircraft that's at Eglin Air Force Base the museum next to Eglin Air Force Base. It has painted landing gear struts. I don't know if that's original for its service. It was also a PB-1Y, similar to how Texas Raiders was at the initial entry to her service. They're actually very similar serial numbers, and they were built in the same plant, so they're pretty close in their age. But she has painted landing gear. Texas Raiders didn't, from what I have seen so far. All of my research has shown that it looks like it's either painted a very, very similar gray to the aluminum color itself, or it is just left as the bare metal. This piece here, being the forward downlock brace, I had the hardest time installing, and you will see it because I left it in the video. I probably didn't include all of it in the video. Anyway, you'll see it, but just a heads up, it's a pain to put into the airplane. One of the new things I'm excited to do for this kit, and I haven't done it yet, but you guys have seen me paint metal finishes before, although I will say it came out particularly nice on this airplane, if I may toot my own horn. But one of the things that I'm excited to try for the first time, and I actually just got them in the mail, I'm going to try some pigment additions, so like some mud pigments that I got from MIG. So I will have that in a later video, because I haven't applied it, I have not got any experience with it, so I'm eager to try it out. And I ended up with a set of aftermarket wheels for this kit after I'd already put them on, so I guess eventually there'll be another B-17. Landing gear, back to doing a chrome finish, so pretty much all landing gear pistons are covered in a chrome plating. The rest of the landing gear is typically not chrome plated because chrome is not good for corrosion resistance for the most part. It experiences a phenomenon called crazing, where it develops microcracking on the surface, and it allows corrosion elements through unless you're doing a post-processing move. So landing gear pistons are usually chrome plated, and that allows them to slide. Chrome's a very good high wear surface. It's a very hard material. So here I am spraying it with a chrome alclad, and the rest of the gear is sprayed with an aluminum alclad finish. So it's a very minute difference, but there is a difference, and it is worth having on the model. A casual note and a warning worth giving people here. I didn't fully appreciate how much discoloration and or removal of the alclad paint would result from handling the part. And so when we get a little bit later into the build, as I'm attaching the wheel with the wiring in it, it was a little finicky. I ended up handling the alclad coated parts with my bare hands a bit more frequently than probably I should have. So the note I would take away, and I'm going to have to fix this later, is clear coat your alcladed parts relatively quickly if you're going to be handling them a lot. It's something that I really should have done. And again, you'll see it later. I end up exposing the primer because I've handled it so much. And I don't know if you caught it there, but I actually peeled a little bit of the alclad off just by removing the tape. Speaking of tape removals, I always find wheel tape removals to be extremely satisfying when they're done very well. And the B-17, the sidewall contour makes it very easy to do these wheels quite well. So I really like the way these came out, and it is super satisfying for me. So the landing gear tires are what I will be working on with pigments in a couple of episodes' time, probably towards the end of the build. Oh yeah. We gotta watch. You gotta watch it again. It's satisfying enough. You gotta watch it twice. But while we do this, pigments on the landing gear wheels is something I'm going to be focusing on a little bit. So that'll be, as I mentioned, that'll be a lot later video, probably as I get towards weathering and once I've got the landing gear wheels all clear coated and protected. And anyway, we now come to the hard part. And the hard part is we need to build this circuit 4 times over, all controlled by the same Arduino, controlling 4 independent motors, and make it all fit inside the wing of the model. Thankfully, 1/48 scale is pretty big for a B-17. Now, I have already done a short on Instagram kind of explaining this a little bit, so who better to explain how this is going to work in a general sense than also me? Alright, before I zip this up, I figured I'd do a short on this and kind of explain what's going on here, and I will put it in the longer video when I finally get that out. So, in order to power the electric motors and the LEDs that will be where the landing light should be, I need power into the aircraft. I need to try and conceal the control board as best as possible. Now, I either have the option of running a giant wiring harness into the model, or I do the electronics inside and only supply voltage, which is what I have elected to do. So, power input will be through the base for the model. There will be some kind of base made, likely to replicate a World War II airfield. It comes up into the bottom of the landing gear tire. The wiring then goes through the landing gear itself, mimicking the brake lines that are actually on the B-17, flows in, up through the landing gear bay, over into a voltage DC to DC buck converter. So I'm taking 12 volts in and dropping it down to 4 volts coming out. Now, this gets a little complex because the fuselage LEDs are stringed together to try and reduce the amount of wiring that's in there. So I have basically 12 volts coming out to the fuselage LED circuit. I also have a 12 volt need to the Arduino Every in order to power it independently without a USB feed. And then from there, I have the 4 volts supplied into these circuits with each of these MOSFET transistors. So the transistors are working as a PWM gate, so each one goes back into the Arduino control board for its PWM cycle. And then I have basically just a standard transistor control circuit. You know, we got a diode, the transistors themselves, and the motors are wired across the diode, positive to negative. So, in fact, actually these wires are driven through the negative because that's the way the propellers spin. So, I'm just about ready to strap this wing back up, and, well, really I need to test it first, which, yeah, it's got me a little nervous, but I think we'll be okay. All right, out. Spoiler alert, it actually did work. So, the brake lines for the B-17, there's 2 of them. In hindsight, one of the improvements I would have made, and you'll see as I build it up, I did put both positive and negative wires in through the same wheel. I think next time I do a 4-engine bomber like this, I'm going to do a positive on one side, negative on the other, and especially because the HKM kit has a relatively large space between the wing root and the bomb bay, where you can sneak wiring in underneath the cockpit floor, it would allow me to transfer that wiring from left-hand wing to right-hand wing with no issues, which is exactly how the motor power supply is. So that would allow me to kind of cut down on the footprint of the electrical harness running up the landing gear because it is a little bit large. So first thing I need to do is absolutely screw up the outer wheel half because for some reason I did that. I'm not afraid to show my mistakes. Pay attention when you're doing wheels, right? So you know this is the outer wheel half because there's no center position for the strut to sit in. And that's where I realized, wait a minute, I got to go back and do this to the inner wheel half. And I later went on and puttied up the outer wheel and re-drilled that hole, and it looks okay for now. It really is fine. It's not that big of a deal. It's not that hard to fix. It was just an annoying moment that I had to overcome. So yes, power into one side, or power into both sides, and cross over to the control board is what I would do in the future. When we get to it, interestingly enough, motor 3, you heard me make the comment that I had to reverse the polarity so positive goes to the negative side of the motor. Except for motor 3. And it's probably because the motors I got are on the cheaper imported side. One of them turns the other direction. So thankfully I tested all of this before I permanently hardwired it all together. But that would have been real awkward real quick if I'd sealed it all together and then had that problem. So test your motors before you put it together. Lesson learned. So yeah, that clip right there is exactly how I ran the wiring through the tire. So when I 3D print the base, I will print out one of the panels effectively more hollow than the other ones. I'll have the power jack sitting at the edge of it. I'll have a switch as well because I don't want to run the motors on this the whole time. And it'll conceal the wiring. It'll look basically like it's a brake line, right? It won't look like there's any electrical attached to the aircraft whatsoever. It'll come straight up through a hole underneath the main landing gear tire that you won't even see. And, for display purposes, it'll look fantastic. The control board being in the wing, you'll see a picture of it here a little bit later as well. With the HKM kit, the kit's very nice because it does allow you to remove the wing as long as you don't glue it in place, right? So the right-hand wing, I noticed, I had a little bit of difficulty fitting it. It didn't really want to slide into place, but I was able to get it there. It just required a little bit more careful pushing. And so the nice thing is that the USB for the Arduino sits facing the wing root. So if I ever want to reprogram it, I can pop that wing off and just plug it in. And you'll see that a little bit later when we get to it. I will also note this is you saw me paint one of the landing gear wheels, or tires. Wheel and tire. This is the other one, obviously. And it's a little bit more complex, so I did paint it separately. Also, at this point, the wiring through that tire makes it hard to adjust in and out, so leave yourself plenty of scope of that wire coming out. All right. Moving on, painting the landing gear with the wires dangling out was entertaining. So if you're doing this, make sure you control that. I had it taped up. I didn't want to paint the wiring too much for the areas that are exposed, particularly the brake line areas. I didn't prime the main part of the wheel here. I probably should have, but I kind of was feeling a little bit lazy. And I'm going to clear coat it anyway. It came out looking okay, but I would not recommend that as a habit. So take it from me. Go out, make sure you put primer down before you do an alclad coat. I got lucky this time. Realistically, I probably shouldn't have. So don't use me as an example for this one. Go back to the previous wheel and use that one as an example. It's much better. So attaching to the landing gear the landing gear struts was a little bit of a pain because I had to make sure that the electrical lines follow the brake hose path. And so obviously the Tamiya super thin or the Tamiya glues aren't going to work very well in this application. CA glue or super glue is going to work a lot better. The brake lines kind of run towards the back of the strut. I had a picture of it earlier, and then they wrap around towards the torque links. If you don't know what torque links are in order to keep the piston that moves up and down from rotating, or in some cases you want them to rotate. It helps work your steering system. So that's what the pieces on front of the landing gear are. Lesson number 74 for this video. Anyway, let's talk a little bit more about the theory behind the electronics here. So for anybody that doesn't know, I did mention a PWM gate in the earlier portion of the short. PWM is pulse width modulation. So what that means is I'm turning on and off the motors very quickly at a certain frequency, right? So X number of times per second, the engine or the motors are turned on, and 1 second minus X is how much of that second they spend turned off. And you make a proportion out of that, and it gives you you're modulating the pulse width of your voltage to your motor, right? This is also how LED brightness is controlled. So, if you were to film an LED bulb that's on a dimmer and dimmer compatible with a slow motion camera, you would see it flashing on and off. And so the concentration of the number of times it's on versus the number of times it's off gives you an overall brightness that our, dumb human meat brains are a little bit too stupid to really process fast enough to see the flickering, as long as it's above a certain frequency. I think your eyes are like 16 hertz is roughly where things become video, and 60 hertz is about where things become a nice smooth continuous process stream for your brain. Here, by the way, is that forward downlock strut that I was complaining about earlier. So that's the forward downlock strut. The link behind it is actually the linear actuator that allows the gear to extend and retract. Obviously the linear actuator is not fully modeled detail-wise because it is relatively small, and it's not really needed, but this was very frustrating. I switched hands. It sits kind of on these three little pedestals that are in the back of the firewall for the engine, and it's just very difficult to put in place. Hello, intern. How are you doing? My intern Mary, who is a cat, is at my feet. Anyway, so back to pulse width modulation. So what the Arduino is doing is sending a pulse width modulation signal out of the contacts that are capable of it, because not every pin on an Arduino is capable of it. For the nano every, there's a squiggle on the ones that are, or like a tilde sign, that is indicating which ones are capable. So your digital 3, digital 5, digital 6, and digital 9 and digital 10 are the only ones capable of doing a PWM. So you get 5 for each Arduino. So it's sending the signal out to the transistor. The transistor is basically working like a switch. So it takes the output from the Arduino, which is PWM, and it's flickering it's opening and closing a circuit based on the PWM signal, which that circuit is the voltage to the electrical motors that are inside the engines as I'm preparing the engines here. And that gives me torque, basically. So a certain frequency will give me enough power to rotate the propellers at a certain speed. And so it works out great. The only thing to remember is that on an Arduino, I think it's 255 is full throttle. So I'm not even running that. I'm running about half power on the finished build, which you'll see a little bit later. So yeah, preparing the motors. One of the things I will note, and I wish I'd done this, and I will be doing it from now on, once these motors burn out, if they're glued in, there is no way to get them out, right? At that point, the model is now a static model. All the hard work is now buried in the wing. It cannot be redone. You're done. It's toast. In the future, instead of gluing them in place, I think what I will do is mount a backstop into the motor, or into the engine, quote unquote, and just interference fit that motor in so that it's really snug against the piece that's in the model. And that way I can pull it out if it ever burns out, cut the wiring, reattach some new wiring, and just slip a new motor back in. And if I've got a programming issue that causes a premature burnout, again, I can pull the wing and I can adjust that. So I'm using the same aftermarket engine pieces that I used on the Memphis Belle. I did adjust the print so that I didn't get the accessory drives on the back of the engine, because it didn't fit in front of the molding for the firewall, basically, on the HKM kit. So it did for Memphis Belle, it didn't for this one. And it was an easy fix. So just something to be aware of. I'm going to post the link where I bought the motor CAD model. But I did resin print it myself. Here for the cowl flaps, the center support section, it doesn't fit with the motor, so I took it out. It doesn't really affect the strength of the model, doesn't affect anything like that. It was pretty easy to get rid of and not have to worry about it. I also didn't show the detailing of the engines. I will say that additional research has led me to believe that the reduction gearbox on Texas Raiders is painted gray. It's not a bare aluminum finish. So I'm going to very, very carefully go back and do that by hand, I think. I'm going to try it on one of the other motors that's not mounted first, because I did many prototypes. And then I will go ahead and add it. So thankfully, assembling these, they're very tight-fitting within the cowling. So they don't move a whole lot, but you want to be very careful about your alignment up and down. The outputs for your ignition wiring, there's a termination to that tube that runs around the front of the reduction gearbox. The terminus of that tube should be pointing up for the 1820, and then I'm super gluing the back just to secure it in place. All right, finally we're on the circuit board. So I'm going to kind of freeze the image here, and we're going to talk about it a little bit more. On the left-hand side, you can see the LED wiring. There's a resistor. You always want a resistor on an LED. That prevents it from overrunning current because LEDs use a very little amount of, or are supposed to use a very little amount of current, but you need a way to limit that because they themselves don't. Then I've got the 4 MOSFET transistors. So these are tip 120 transistors. And then I've got a diode for the motor to prevent it backdriving and damaging the transistor or the Arduino. And then I've got a common bus of positive and a common bus of negative, and the engines themselves are wired across the transistor. And so the transistors are independently allotted to one of the PWM drives on the Arduino, and then the Arduino code I have put in the description. If anybody has any questions, please feel free to leave me a comment. I am more than happy to help anybody else do this because I think it's really cool, and I've put a lot of time into it, and I think the best value I can take from it is by helping another person do it. So leave me a comment, and for now, because this absolutely is a cliffhanger finish on this video, you can watch my initial test of the first 2 motors running a startup sequence. I'll leave it right here on the screen now. If you've stayed with me, thank you so much. Feel free to like, subscribe. Again, I'll remind you, comment, say hi, whatever you want to do. I'm more than happy to help anybody else do this. And in the next part, which will be coming imminently very, very soon on the heels of this video, you'll see the full up, all 4 motors turning, running a full test cycle. Stay tuned. I hope you've enjoyed this. Catch you guys later.